Okay, so this week we'll be doing the lab activity, simple harmonic motion. So you click on this file and you're going to see, let me bring up the file. You are going to see this. All right, so simple harmonic motion, and it describes a simple linear oscillator that is making periodic motion. So the experimental setup is like this. So you have the a stand, and on the stand you're going to put a force sensor, and on the force sensor you're going to put a spring, and on the end of the spring you're going to attach the mass solder to that. And then so because because the mass on the spring, so the spring is going to be stretched. Before you do any experiment, you want to you want to zero the sensor. In other words, you want to calibrate. So when you calibrate, you want to calibrate the force sensor when the mass holder is on the spring. And once you zero the sensor, then you start adding mass to the spring, and then the spring is going to be it's going to be stretched because of the force, because of spring force, which is equal to, if you remember, F is equal to negative K, which is the spring constant, and then time X, and X is the displacement. So the more forces on the spring, the larger the displacement, and the force comes from the mass you add on the mass holder. So this experiment has two things that you want to do. The first thing is that you want to find the spring constant of the spring, and as I mentioned, because spring constant can be found by adding the masses on the mass holder, and the equation that is based on is this. So this is K, and this is X, and X is the displacement, although in this case that will be the vertical displacement. So you can see that the amount of force that you add on the mass holder is proportional to the displacement. So you're going to add 20 grams increment each time, and the motion sensor is going to sensor the position of the mass holder, and then you're going to continue to add masses. So this mass holder is going to get closer and closer to the motion sensor, and then once you have the force, and then you have the displacement, then you can plot force versus displacement. Okay, and of course, recognizing that you have the negative here, so we're actually just going to use absolute value of the force plus and plot against the absolute value of the displacement. So then the slope that you get is exponential value of the spring constant. So we're going to the first part of the experiment is to find the spring constant by utilizing this expression and by adding masses on the mass holder, and by measuring the position. So during this experiment, the motion sensor, which is the motion sensor, which is this one. Okay, so it's going to be sensing the position of the mass holder. So this is not the displacement. So what exactly is the displacement? The final position minus the initial position. That's how you find the displacement. Okay, and once I show the data, then I'll say that again. So so the first part involves this, just finding the spring constant. And once you find the spring constant from the first part, and then you're going to use that spring constant for the second part when you're ready to find the period. And so once you finish with the first part, then the second part is that we're going to put 100 grams mass on the mass holder, and we're going to pull the whole thing down, and then we're going to release it. And then once we release it, it's going to oscillate. And when it oscillate up and down, so because this is a spring and exerting a restoring force, so the whole thing here is going to go up and down, and the motion sensor is going to sense that, and the computer, the software is going to measure position or the displacement, amplitude, It's going to measure the displacement and also the measuring the velocity, how fast the whole thing is oscillating up and down. And so you're going to have the position as a function of time. You're going to also have the velocity as a function of time. And based on these two graphs, you're going to figure out the period of the simple harmonic motion. And the period theoretically is this equation. So the equation is theoretical period can be found by using this equation, which is 2 pi square root of mass over k. And the k here is a spring constant, and the mass is whatever's on the spring, okay, which will be given. And so once you have that, you can calculate the theoretical value of the period and then compare to the experimental value. So that's basically the overall things about this experiment. First thing is that find the spring constant of the spring, and then you put 100 grams of mass, and you have to kind of make changes to the program so that it will continue to measure the oscillator as a function of time. And when you do that, you're going to see a graph like this. And so take, for example, this is position on the vertical, that's position, and on the horizontal, that's time. So if you were to do this experiment, you will use this, what we call the smart tool, of the program, and then put that the coordinate on top of each peak. Let's say we put on this, and we have a time, and we will call, if this is your first peak, then we call that T naught. And then you move this coordinator to the next peak, which is this, and then you measure the time, record the time, which you call that T1, and you do this next one, and then T2, and so forth. So this T naught, T1, T2, and so forth until you reach the, let's say, T11. So you're going to have 11 data points, and this 11 data points indicate the times when the oscillator reached the peak value. So these times are not periods. Periods is defined as the time that the motion repeats itself. So it will be the time difference of this. Let's say, so the period will be T1 minus T naught, and then the period, another period that can be obtained by doing T2 minus T1, and then T3 minus T2, and so forth. So you can see that, the time difference refers to the period. So you have 11 data points, which means that you're going to collect 10 periods. Okay, so you're going to collect 10 periods from the velocity plot. You're going to get 10 points from the 10 periods from the position plot, and then you're going to take the average of the time, the periods, and then you'll get one average, and then from one plot, and get another one for another data set. And so the final experimental value can be obtained by averaging the two averages. Okay, so that's basically the overall, that's basically the whole what you want to do. So let's see. So altogether, you should have only one plot, and that plot is from the first one. When you plot force versus delta x, okay. And so this is the data that's in the lab packet, and then you can see that you're going to calibrate the sensor when the handle is on, and then you add 20 grams to the mass holder, and then the force sensor is going to register the force, and the motion sensor is going to register the position of the mass holder. And sometimes you want to make sure that the motion sensor is directly under the mass holder. Otherwise, the motion sensor might sensing the ceiling, and that happened to previous classes when they did not place when they did not check that the motion sensor is directly under the mass holder. And then the second page that shows the time where when the oscillation reached the peak. So these are the times, and then based on the times you can calculate the period. So this So this first box here will be T1 minus T0, and the second one will be T2 minus T1, and then T3 minus T2, and so forth. Okay, so these are the data, and then from the M and K, and then you can calculate that. So bring up the let me bring up the table, the data. So the data, let me see if this is the one, this one. All right, so the data will be in Word document, so we need to key in the data to the Excel. And as you can see, when you zero sensor, the first value of sensor, the first value of the force should be 0, and this 0.704 indicate the position of the mass holder. And when you keep adding masses, you can see that the position is getting smaller because it's getting closer and closer to the motion sensor, right? And regarding the displacement, your T naught, your X naught here is your initial position, and all the subsequent values are your final position. So you will use the final position minus initial position, to get the your delta X. So your delta X should be getting larger and larger, okay? Because with the more masses, the displacement should get larger as predicted by the spring equation. F is equal to negative kx. So you want to make sure that delta x is getting larger and larger, and as I mentioned, when you use the final position take for example, the final position minus initial position, you're going to get negative value. But because we're only using the absolute value, so you use the plot the force versus absolute value of delta x. Okay, so that refers to the first part of experiment. And the second part of experiment, so you can see that all these terms are given, and you need to figure out the time difference. So time difference will be the difference between any 2 points. So this will be 2.49 minus 1.3, and this one should be T2 minus T1, and this one should be T3 minus T2, and so forth. And then once you have the 10 data points, you find the average of that 10 data points. So you have one average from the position versus time plot, and another so the figure will not be figure are not provided to you. You'll just be provided with the data points. All right, so there's no figure for that for this too. And then you have the velocity versus time, do exactly the same thing, and you have another average here. So you have one average, one average. And so experimental value of the period will be the average of the 2 averages. And then theoretical, you use equation 1. K is from from your figure, and mass is 100 grams, 100 gram plus 5 grams. So you should put 105. Okay, I think. Yes, I think it's 105. If there's a difference, then I will put it in my weekly announcement. And then from this two values, you can calculate the percent error. Okay, so that's basically what you want to do, for this experiment. So again, the data are provided in the Word document. You need to key in the data points to the Excel and use Excel to process the data. And then if you organize your data in a very well presented way, then you do not have to show this data table in your in this way to again. But if your Excel file, if you organize your data in Excel not so well organized, then I would strongly recommend you after you're done with Excel, then key in the your results in this tables, and then present it in your data analysis, so that it will be easier for me to get your to look at your results. Okay, and also when you use Excel, sometimes the borders, the lines are not shown, so sometimes it will be kind of difficult for me to look at which one is for which. Unless you use if you use the borders, then I will know what which data point is for what. Okay. And so for this one, let me see. So simple calculations, very easy. You just need to show how you got the delta x. Just show one, okay? And then the periods, the periods, uh, the average is, you're going to use Excel building function. So I think you don't have to show that. Um, you do have to show how you got the theoretical value of the period and the final value of the experimental value of the period and the percent error. So sample calculation, there's just a couple of equations. Regarding sample calculations, again, I noticed that quite a few students, they did not follow the required, steps. So for any sample calculation, you should have the first line is the equation. For example, the equation, if we're using t equals 2 pi square root n over k, then you should write that equation. And the next line will be your t is equal to 2 pi and then times square root of the mass that you use, the mass value, for example, that's 0.105 kilogram, and over k is, let's say, 3 point something. And then, so those are the value that you use. And the third line will be the data, the results, okay? So you should have like break it into 3 steps. And, some students, they only have the numbers, the second step, missing the equation. And, or some students only list the equations, but without showing the value that they use, which will be okay only if your results are correct. Now, sometimes the students, they have incorrect values. Then if you don't show what you have, then it's very difficult for me to check whether which part that went wrong. And that goes for the same applies to your when you take the test or when you take the quiz. When you want to show your work, you should have the equation, the number you use, and the results. That will increase the number of points that you can get. Otherwise, I have nothing to go by, And then if you did it wrong, I just have, then I will just have to mark it wrong. Okay. All right. So that's basically what you want to do for this experiment, for this week's experiment. All right.